All right, Chemistry 3111. This is the last of the humongous chapters, I would say, in this class. Chapters 18, 19, 20, all massive, a lot of content, extra time allotted for those. So chapters 18, 19, and 20. And yeah, so now we're into chapter 21, which is the last of the really long ones, which deals with alpha carbon chemistry, enols and enolates. Okay, so let's start by talking about alpha carbon. If you remember when we talked about alkyl halides, so when we talked about alkyl halides, right? Let's say you have something like this. Okay, you have one bromopropane or something like that. We call this the alpha carbon. Okay, the carbon that is attached to the bromine. However, when we're talking about enols and enolates, in this chapter we're going to be dealing with carbonyls. Okay, so a lot of carbonyls. And the carbon that is directly attached to the carbonyl carbon, that's the alpha carbon. So these would be alpha carbons. Okay, so just a little bit of a different way of thinking about it when we're talking about carbonyl compounds versus alkyl halides. So Greek letters, we use those to describe the proximity of carbon atoms to the relative carbonyl group. Right, you guys know that when you have a carbon with a double bond to oxygen like this, right, this specific part of the compound, this is called the carbonyl, right? And you find carbonyl groups you find carbonyl groups. So we'll just circle it again here, and I'll just say, there we go, carbonyl. And we find carbonyls in aldehydes and ketones. We also find them in carboxylic acids, esters, and amides, etc. But again, the point of this slide is that the carbon that is right next to the carbonyl carbon, we call that the alpha carbon. After alpha, you have beta, then you have gamma, then you have delta, so on and so forth. We're only going to be concerned up to the delta carbon, for maximum. But again, what are we concerned about in this chapter is we're going to be talking about reactions that take place at the alpha carbon. So this whole chapter is going to be alpha carbon this and alpha carbon that over and over and over. Well, let's start by looking at those alpha protons that are attached to the alpha carbon. So if you take this molecule here, this is just acetone, nail polish remover, right? You guys know that there are a total of 1, 2, 3 protons attached to that carbon. There's also 3 protons attached to that alpha carbon as well. And so what it's saying here is if you put this ketone in a catalytic amount of acid or base, you end up with some of what's called the enol. Okay, now where does the word enol come from? Well, you can imagine that on this carbon, you have an alkene. So alkene, so that's where the ene comes from. And then on that same carbon, you also have an alcohol. So that's where you get enol, is because you have an alkene and an alcohol on the exact same carbon. So we see that the enol can undergo a reaction to install a halogen at the alpha carbon. And then if you put the ketone in a strong base, that's going to deprotonate completely to produce what's called an enolate. Okay, and the enolate, of course, it has another resonance form, which we're going to take a look at later on. But the point of this slide is this: is what we're going to see is we're going to see a whole bunch of different reactions in this chapter, a plethora of them. But the reactions that are covered in this chapter are either going to proceed through an enol intermediate or an enolate intermediate. We're always going to see one of those somewhere along the way. So let's start by talking about enols, and then we'll get into enolates a little bit after. So again, what did it say right here? It said if you take a ketone or an aldehyde and you put it in the presence of a catalytic amount of acid or base, you end up with the enol, and there's an equilibrium here between the enol and the ketone or aldehyde form. So let's take a look here. So if you have acetone, which is a simple, I guess the simplest ketone you can have, you see its enol form over here. Again, it says there's an equilibrium between the ketone and the enol. You guys know what equilibrium is. And you should know that the difference between the ketone form and the enol form, because we've seen the enols before in this class, is that these are tautomers of each other, okay? So if you've forgotten that word, you need to remind yourself of what a tautomer is, okay? The definition is this. Now, you can look it up in the textbook, but the difference between tautomers is this, is they are isomers, okay? They're isomers that differ in the placement of two things, a double bond, okay, and a proton. One of the protons from here is now over here. So again, I'll repeat that. Tautomers are isomers that differ in the placement of a double bond and a proton. And again, this is something that we covered way back in Organic Chemistry 1. We looked at enols and tautomers for the first time actually in Chapter 9 when we talked about alkyne chemistry. Anyhow, if you look at the equilibrium here, okay, so this is called cyclohexanone, okay? You can see its enol form is over here, but if you have a bottle of pure cyclohexanone, so cyclohexanone is a liquid at room temperature, if you actually studied or were able to analyze, that bottle of cyclohexanone, you'd see that greater than 99.99% of the molecules, so that means that, out of 10,000 molecules, 9,999 of them would be in the ketone form, and very, very few would be in the enol form. So in general, this is a rule too. Equilibrium generally favors the ketone. Of course, as one of my students wrote me a number of years ago, he sent me a meme which said, what did I learn in organic chemistry? A whole bunch of rules and then the exceptions to those rules. Well, we're going to look at the exceptions in just a second. But what I want you to remember is that these are not resonance structures, okay? And I'm sure that you know that already and you're, fully aware of that. These are not resonance structures. These are isomers of each other, okay? They're just constitutional isomers, tautomers to be more specific. But a number of years ago, I had a student ask me, the resonance structures. I said, no, these are not resonance structures, right? This is an equilibrium, okay? So these are not resonance structures. Well, let's take a look at some of these exceptions where the equilibrium doesn't necessarily favor the ketone that we can see the enol form favored. Well, there's two specific examples that we take a look at in this class. The first one is what we call a 1,3 diketone. Now, you can imagine why this is called a 1,3, right? If you wanted to give this compound a proper name, you would start numbering here 1, 2, 3, 4, 5. So you'd call it 2,4 pentane dione. That's the proper name. I agree. There's nothing wrong with that. However, if you look at the carbonyls, you see they're spaced, one carbon apart. So that's where we get the word or the name 1,3 diketone. Well, it turns out that if you form the enol out of one of those ketones, you end up with a 1, 2, 3, 4, 5, 6-membered ring where this bond is actually a hydrogen bond, okay? And you guys know that hydrogen bonds are the strongest type of intermolecular force that we look at, and that 6-membered rings are highly stable in organic chemistry. So what does that tell you? It provides you with a rationale as to why when you have a 1,3 diketone, the enol form actually predominates. Okay, so this enol form, okay, this predominates. You see it's 70 to 90%, whereas the diketone form is only about 10 to 30%. Okay, so there you go, a little bit more stable than a typical enol. And again, what's the giveaway? It's the hydrogen bonding, which would be the driving force there. Another one that, there's no no-brainers in organic chemistry, but you guys know enough to know that aromatic compounds, right? Aromatic compounds. What does aromatic mean to us now? It means stable, right? So if I look at this compound here, and that's the ketone form, and then I look at the enol form, well, you see that this compound here, this is phenol, okay? Now, phenol does have a ketone form, but you can see that the phenol is aromatic, whereas this is not aromatic, right? You have an sp3 hybridized carbon right here, and so this is not aromatic whatsoever, okay? It doesn't have anything to do with aromaticity, so of course the equilibrium is going to lie to the side of the phenol. But again, these are the two exceptions you need to know. So one would be this one here, the 1,3 diketone, and the other one would be phenol, right? It's a very specific compound. And you had to memorize the name of phenol way back in chapter 17. So phenol isn't anything new to you at all. Now, one thing I always try to do with my students is tell you, these are the mechanisms that you're responsible for. These are the ones that you will never be asked in this class, okay? Well, one mechanism that you're definitely, or two mechanisms that you're definitely required to know would be the acid catalyzed tautomerization, which is shown on this slide, and then base catalyzed tautomerization, which is shown on this slide, okay? So acid and base tautomerization, you have to know these mechanisms. Everybody does. All the organic chemistry students have to learn them. The good news is that they're not long. They're very, very short, okay? So how do we have this equilibrium between the ketone and the enol form? What's the mechanism? Well, the first step is the proton transfer, where you protonate the carbonyl. Okay, so we protonate the carbonyl. You guys know that this oxonium is resonance stabilized, so we have these two resonance forms here. And after the hydronium loses its proton in the first step, water is the conjugate base of hydronium. So water, even though it isn't a strong base, it's going to behave as a base in this case, and it's going to remove this alpha proton, and it's going to restore neutrality. And there you go. Here's your enol form like this. Now, again, this is a very important mechanism for you to know. The acid catalyzed tautomerization of a ketone to, or an aldehyde to, an enol. I told you also have to know the base catalyzed tautomerization, which is shown on this slide. So I'll put a little red star on this one. Usually my sign for have to know this mechanism. Now, in this case, the first step is a proton transfer, but it's not protonating the oxygen of the carbonyl. It's a deprotonation, right? Because we're in a strong base, like sodium hydroxide or potassium hydroxide. So it's going to abstract a proton, and we end up with a resonance stabilized anion. And then now water is going to come in and behave as an acid in this case. It protonates, and we end up with our enol. Okay, we end up with our enol. Now, if you look at that resonance stabilized anion, you can see here that this looks like an ene, and then it's like an ol, but it's missing the hydrogen atom on the oxygen. Well, you guys know enough to know that when you have something that has a negative charge in chemistry, it oftentimes ends in ate, sulfate, nitrate, carbonate, oxalate, etc., etc. And so we actually call this resonance stabilized anion. We call this, it's got a name, we call this the enolate. Okay, so enol and the enolate. Okay, so we're going to look at both of those. And if you go back to the whole idea of the enol, so here's an enol drawn right here. It says it's safe to assume that some fraction of the ketone slash aldehyde in solution will exist in the enol form. Okay, even if it only exists a little bit in that form, take a look at the electrostatic potential map of the enol. So here's your enol, right? This is just a resonance form. There's nothing wrong with this resonance form whatsoever. But what do you notice is that one of the carbons, and they're just showing this one here, happens to be electron rich. So when I think electron rich, I start thinking, okay, if something's electron rich, is it nucleophilic? And the answer is yes, it is. So it turns out the enols are actually nucleophilic, okay, by the alpha carbon. So the alpha carbon of an enol can be nucleophilic. And we're going to see this over and over and over in this chapter. So if you're not picking up on it right away, trust me, you're going to see it enough that you're going to pick up on it. Now, if you look at the enolate, right, if you go back to the enolate, well, that's got the negative charge baked right into it, okay? So I told you that this is called an enolate, right? You see negative charge here. So it turns out that an enolate is way more nucleophilic than an enol because it has an overall negative charge. Now, I'm going to go back in the slide, so just bear with me. Watch. I'm going to go all the way back to the very beginning, okay? Way back to the first slide, okay? Remember, in the first slide, I showed you an enol, okay? And I showed you an enolate. And then it even shows you on this introductory slide, it says, oh, you can put things at the alpha carbon, whether it's from the enol or the enolate. Either way, you can end up with, see, there's an arrow here and there's an arrow here. You can functionalize at the alpha carbon. So now what it's saying is the reason why you can put in a group here like a halogen is because an enol is nucleophilic and an enolate is nucleophilic, right? So we looked at the reasons why an enol is nucleophilic. So let's go back. Why is an enol nucleophilic? Well, you look at the resonance forms. You see we have a negative charge right here. You look at the electrostatic potential map. You see delta, you say delta minus here. So yeah, an enol is nucleophilic. But then if you look at an enolate, well, again, it's got a negative charge overall. So that's going to be much more nucleophilic than an enol. But again, they're both nucleophilic, but an enolate is much more, or it's a much stronger nucleophile, much more nucleophilic. Okay, now I know you're all very astute, so you might be looking at this enolate and go, well, dang, you know what, Mr. Dion, there's the problem here. This carbon could act as a nucleophile, and this oxygen could act as a nucleophile. So which part's going to do the nucleophilic attack? That is an awesome, awesome question. Okay, so that's a great question to come up with if you're thinking of that. And the answer is it actually can do both. Okay, so an enolate, sometimes it does what we call O attack, where the oxygen acts as the nucleophile, and then sometimes it does C attack, where the carbon is your nucleophile. Okay, however, it's that generally speaking, enolates undergo carbon attack or C attack. Okay, which you can draw the way that it's shown here. There's nothing wrong with this. Or you can draw it using two curved arrows like this. Both of them are acceptable. I would say that I remember one time I taught this chapter and I said to my students, oh, I'm going to draw it this way every time. And then I started teaching it and I'm like, no, I didn't. I probably split it. So I think I probably used this some of the time. And I think the textbook uses this a lot of the time. So I try to follow our textbook. So um, now what's the point here? Okay, a couple of things. Number one, in our textbook, we're really only going to be looking at carbon attack. Okay, this is what we're going to study in chemistry 3111. We're not going to look at O attack. And most of the reactions, not all, but the majority of the reactions in this chapter are going to involve enolates. So again, there's enols, they show up a lot, but enolates show up even more in this chapter. Okay, now let's talk about how do you make an enolate, right? Because you guys are perfectly aware that if I take my aldehyde like this one and I treat it with a base, right, it's going to rip off this proton and I'm going to end up with an enolate. So I'll just draw, come on, Apple Pencil. I'm going to draw the enolate that you would get. So you'd have the negative charge like this, okay? So is that an enolate? Absolutely. Could you draw the resonance form? You bet your Bobby socks you can, okay? So yeah, that's how you make an enolate. But the question is, how do I pull off that proton? What kind of base am I going to use? And that's kind of what we're going to uncover right now. Now, also, the beta and the gamma protons, those are not acidic. Why not? That's a really good question. Sometimes you might wonder, well, why don't I pull off one of these or one of these? Well, the answer is they're not as acidic. They have a higher pKa, and the reason is that if you pull off one of the protons or one of those protons, the beta or the gamma, you end up with something that is not resonance stabilized. It does not yield a resonance stabilized intermediate if you pull off the beta or gamma protons or delta protons, whatever. It's the alpha protons. Why are they so special? Why do we focus on them? Because when you deprotonate, you end up with something that's resonance stabilized. Okay? Give me a thumbs up if you're with me so far. You're like, yes, enolates are resonance stabilized. That's cool. Okay, I haven't taught you how to do the deprotonation yet. We're going to get into that in dirty detail in just a second here. But let's take a look. Every once in a while, somebody will ask, oh, do you have a table that summarizes all of this? Well, this is the first table in the textbook, and it doesn't summarize everything, but it's kind of a refresher on pKa's, okay? So if you've forgotten the pK of a ketone, so these are both ketones, acetone and acetophenone. These are ketones, and I know you don't need help with that. But the ketone has a pKa, generally speaking, around 19. So you see acetone is 19.2. Acetophenone is around 18 and a bit. And then an aldehyde, you see acetaldehyde is down here. It's got a pK of around 17. But either way, I mean, as long as you know high teens, it's good enough. And then somebody took the time to draw the enolate forms of all of these and drew the resonance forms for each one of these, okay? So you could take this compound that I drew up here and you could try and draw its resonance form. So let me get a black pen, but you could practice doing that and you'd say, okay, well, I'm going to end up with a negative charge on my oxygen, a double bond here like that, right? So that would give you a little bit of practice. So there are some practice problems in the textbook where it says, draw the enolate, and we're going to get some practice on that today as well. So now that we have a little review of the pKa's of ketones and aldehydes, let's talk about something that might be an appropriate base. What's one of the most common bases that we see in this class? If you think about wanting to form Zaitsev alkenes, for example, who remembers this chestnut? Sodium ethoxide. Did we use that Avogadro's number of times in Organic Chemistry 1 or what? The answer is totally. Now, if you're wondering, would ethoxide, so this is ethoxide, the sodium has been left out here because it's a spectator ion. Is ethoxide a good base to deprotonate this, this aldehyde, this is acetaldehyde, to make the enolate? Well, the answer is in examining the acid, the base, the conjugate base, and the conjugate acid. If we compare the two acids, you see that the acetaldehyde has a pK of around 17 and the ethanol has a pK of around 16. So the equilibrium is going to lie to the side of the weaker acid. So this is the weaker acid. And so what does that tell you? It tells you that, yes, ethoxide and alkoxide can deprotonate some, but it's certainly not going to deprotonate everything. Okay, now if you're just thinking, okay, so my conclusion here is ethoxide is a crappy base, or it's not strong enough to deprotonate this to make the enolate, right? This is my enolate. That's partially true. However, think about this. If you were to mix acetaldehyde and ethoxide, what do you actually have? Since it's at equilibrium, that means you have some of the aldehyde and some of the enolate in the same flask. Let me draw them. You have some of this compound and you have some of this compound in the same flask. This is a nucleophile. This is an electrophile. So what that means is that they can react together. Now, that's not my best curved arrow, but you can get a nucleophilic attack by the enolate on the aldehyde like that. And that's something that we're going to take a look at in just a second. So we're going to cover that in section 21.3. So I'm just going to move this out of our mind's eye. I'll stick it down there. We're going to see that in section 21.3. Well, what about a base like sodium hydride? Okay, NaH, that's a pretty strong base. Well, if you were to use sodium hydride as your base, so let's see here, acetaldehyde, that would be your acid. This would be your base. Excuse me. This would be your conjugate base. And your conjugate acid in that case would be H2 gas. And H2 gas has a pK around 35. So its pKa is around 35-ish. And the pK of this was 16.7. So what does that tell you? It tells you that the equilibrium is going to lie to the side of the weaker acid. So is hydrogen gas an effective base at deprotonation? Absolutely. It's going to give you 100% deprotonation, right? Another reason why is because hydrogen is a gas, so it's just going to go up the smokestack up into the atmosphere. It's not coming back. So this is an irreversible reaction. So what does that tell you? Sodium hydride is going to do complete deprotonation, whereas something like sodium ethoxide that we saw in the previous slide, that's only going to do partial deprotonation. Okay, so what's another strong base? So sodium hydride isn't new to you, but this one is, okay? If you take diisopropylamine, I know we haven't done amine nomenclature, but you guys know what an isopropyl group is, right? There's two of them, so we call this diisopropylamine, okay? It's just a base that you can buy. It's relatively inexpensive, and this is called butyllithium. Butyllithium. Sometimes it's called N-butyllithium. Either one is fine with me. But anyhow, if you take N-butyllithium, which is a very strong base, okay, just put here, very strong, okay, very strong base. It's going to deprotonate your diisopropylamine to give you what's called lithium diisopropyl amide, or it's more commonly known as LDA. Now, LDA is like sodium hydride. It is a very, very strong base. And you guys probably remember that the pK of an amine is something like, it's in the high 30s, something like 36 is what it says over here. So if we were to use LDA as our base, and here's our aldehyde here, this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid. Well, which side is the equilibrium going to lie to? It's going to lie to the side of the weaker acid. So there you go. So that means that LDA is going to be effective. It's going to completely deprotonate all of your aldehyde or ketone to make the enolate. And so another thing is that LDA, because it's got these big bulky isopropyl groups on it, it's really good at deprotonating. It's a very good, terrible nucleophile because it's just too sterically hindered. So what's our conclusion from all of this? Let's see if we can, before we do that, I have one more thing I want to show you. Sorry, I forgot. There's one more thing. You remember that 1,3-dicarbonyl that we talked about a few minutes ago? So we called this the 1,3-diketone. Okay, if you're just about with respect to that, if you compare that the 1,3-diketone, if you compare these alpha protons pKa with that of an aldehyde or a ketone, you see it's way more acidic. Okay, much. It says here. Look, I'll highlight it. Much more acidic. Well, why would that be? It's because of more resonance stabilized. Okay, and when I talk about that, I'm talking about the conjugate base. Okay, so if you draw the conjugate base down here, you can see it's got 3 resonance structures. And so that's why it's so acidic. It's just got extra resonance. And so, yeah, so if you have a 1,3-dicarbonyl, what's the conclusion? Do you need to use sodium hydride or lithium diisopropylamide? I would write here NaH or LDA, not required. Why? Because it's so darn acidic already that even if you use a weaker base like sodium methoxide, it's going to completely deprotonate the 1,3-dicarbonyl. Why? Because the equilibrium is going to lie to the side of the weaker acid. Again, this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid. So the equilibrium is always going to lie to the side of the weaker acid. And so it would be overkill. I love the fact that he uses this word here, that sodium hydride, let me use a pen, sodium hydride or LDA would be overkill when you're dealing with a 1,3-dicarbonyl. All right. So what's the conclusion? The conclusion is this. If we have an aldehyde or a ketone, so we'll put here aldehyde or ketone. If you want to do partial deprotonation, you would use a base like sodium hydroxide or sodium methoxide. That way you're going to have the enolate and the ketone or aldehyde form together, right? And again, I said we are going to discuss this at length in section 21.3. If you use a really strong base like sodium hydride or lithium diisopropylamide, you get irreversible enolate formation, so you only have the enolate, nothing else. If you have a 1,3-dicarbonyl, so again, this is called the 1,3-diketone or 1,3-dicarbonyl, either one is fine, okay? In that case, LDA or sodium hydride, not required, they're overkill. Let's put that word over here, overkill. Don't need a base that strong. In that case, if you use something like sodium hydroxide, okay, either one of those would be overkill, so they're not required at all. You can use a weaker base like hydroxide or ethoxide, and that will give you nearly complete enolate formation. So what have we covered? We've covered what an enol is. We've covered what an enolate is. I said that when we do alkylation or halogenation at the alpha carbon, it's going to be at the carbon, not at the oxygen of your enolate. We said if you have an aldehyde or a ketone, if you use sodium hydride or lithium diisopropylamide, it gives you complete formation of the enolate. If you use a weaker base like an alkoxide or hydroxide, you end up with a mixture of the enolate and the neutral form. And then if you have a 1,3-diketone, in that case, a weaker base is good enough and it will give you complete deprotonation. All right, so now that we've got that done, question 21.6 is a good one because it gives us a chance to draw some enolates and just kind of flesh that idea out before we start putting groups at the alpha carbon. It says draw the enolate that is formed when each of the following compounds is treated with sodium methoxide. In each case, draw all resonance structures of the enolate ion and predict whether a substantial amount of the starting ketone will be present together with the enolate at equilibrium. All right, so we're taking this compound here. We're going to treat it with sodium methoxide. I'm going to leave the sodium out because it's a spectator ion. This is an alpha carbon. And this is the only type of alpha carbon in here, right? Because we've got a plane of symmetry this way, and we have a plane of symmetry this way. So there's literally just one type of alpha carbon in this entire molecule. And so my base is going to pull off my proton, and I'm going to draw the enolate that I get. So let's draw the enolate. So we get something that looks like this. And then it asks us to draw the resonance form. If we want to draw the resonance form, we're going to make a double bond, put a lone pair up here, and then we end up with something that looks like this. The negative charge on our oxygen, like that. Okay, there we go. So am I going to have an appreciable amount of both of these? Or am I going to only have the enolate in this case? Could anybody tell me? Will I have both or just the enolate in this specific case? Keep in mind, sodium methoxide is not a super strong base. Could anybody tell me, would I have both or just the enolate in this case?
Would you have both of them?
Absolutely. Yep, totally. The reason you would have both in this case, okay, we'll put here both are present at equilibrium, like that. And the reason why is because the pK of this proton is probably around 17-ish, okay? And the pK of ethanol is around 15-ish. And so, what they're trying to get you on this one is that sometimes students will see the 2 carbonyls and they'll be like, oh yeah, it's going to deprotonate everything. Keep in mind, this is a 1, so this is a 1-4 dicarbonyl, not a 1-3, okay? So if the compound had been this, if they had given you this, in that case, it would be completely deprotonated, but in this case, it will not be. So great answer. All right, let's try the next one. So we have isopropyl phenyl ketone. If we were to treat that with sodium methoxide, there's only one beta proton, or one alpha proton, excuse me, in the whole thing. And it's this one here. So if I pull that off like this, I'll draw the enolate. So we'll draw the enolate. First, we'll draw it with the negative charge on the carbon, like this. All right, so we'll draw it like this. And then we'll draw the resonance form. So just put a square bracket, and we'll draw the resonance structure. So we put the pi bond here, put a lone pair up here, and we end up with something that looks like this. So where we have our double bond here, and now we have our enolate, just like this. Now in this case, again, you're going to have an appreciable amount of both. Both are going to be present at equilibrium, so both present at equilibrium. And the reason why is the pK of this proton is going to be around 18 or something like that. And the pK of ethanol is around 15, 16, something like that. And so they're very close. And so, yeah, you're going to have both of them present. And so for both of these, we can draw equilibrium arrows for both of them. I know these aren't perfect equilibrium arrows, but you get my drift. Maybe I could fix them up a little bit. There we go. There you go. So both of these are going to be at equilibrium. All right. But again, if it was a 1,3 dicarbonyl, and I think that's one of the questions in the textbook, if you took this and you treated it with ethoxide, in that case, it's going to 100% just give you the enolate. So all you would have is the enolate, okay, plus ethanol. It's going to lie to this side. All right. And that's the reason why is because the pK of this proton is around 9 or something like that. Again, that's one of the questions in the textbook. I have it written down here, but I can't read my own writing. I think it's question A. I think it's actually question A, which is this question here. So make sure you take a look at that one. But let's move on from there. So everybody with me on the first part? So that's section 21.1. So just talking about, it's really kind of figuring out what's an enol, what's an enolate, what are the pKa's of ketones and aldehydes, just to review that. What's a good base for deprotonation? If you want to deprotonate completely, use a strong base like LDA or sodium hydride, unless you have a 1,3 dicarbonyl. And sodium methoxide will give you a mixture of both the enol and the ketone form or the aldehyde form. All right. So with that in mind, let's try our first reaction. Okay, so far we haven't really learned any reactions, and there are a whole bunch of different reactions. It's always murder to do this, but I'll just scroll down to the bottom with you guys. If you go down to the very bottom, he actually does a really good job of summarizing all the different reactions that are covered in this textbook. We're going to do this one first. This is where we start, is with what we call alpha halogenation. You can see where it comes from with the alpha carbon. You put a halogen there. And then we're going to get into a reaction called the Hell-Volhard-Zelinsky. How's that for a name? Okay. Anyhow, sometimes we call it the HVZ reaction. And then we're going to get into the haloform reaction, which is a really important reaction. I'm not going to mention all these right now because I don't want to flood your brain, but you see that these are the reactions that are covered in this chapter. Okay, then we cover these things: alkylation, malonic ester synthesis, Michael addition, Stork-enamine, Robinson annulation, and all this stuff. But again, we're starting with the reactions right here. Okay, this is where we're going to start right now, is with what is called alpha halogenation. So let me back up, and we're going to use this whole concept of enol and enolate in this portion, of course. All right, so it says here that under acidic conditions, ketones and aldehydes undergo alpha halogenation. So let's see what we have here. We've got a ketone, we've got an acid catalyst. Okay, so this is acid catalyst. How do I know it's a catalyst? It's because it's in square brackets. And then I have bromine. And then somehow magically I end up with a bromine at my alpha carbon, and I release some HBr. Now this reaction works with chlorine, bromine, and iodine, but not with fluorine. Fluorination, as you can guess, is too violent. Okay, so it's not really a good way of doing it. But if we're in acidic conditions, you guys saw the mechanism for the acid catalyzed tautomerization. So that means that the enol form, right, if we are starting out with the ketone, right, and if we have some H3O plus in there, that means that somewhere along the way, we must have the enol form. Okay, and what we're going to see, and the mechanism is just that. Okay, so this is the mechanism that we already looked at. Okay, you say see previous slides. Okay, I actually told you had to know this mechanism. So the formation of the enol under acidic conditions. So really the only new part here is going to be this part down here. So check it out. It's very quick. It's only 2 steps. The first step, you guys know that bromine, Br2, is polarizable, right? You guys know about bromonium ions and all that stuff. So the enol is not a strong, super powerful nucleophile, but it's strong enough to attack the bromine, which is polarizable. We add the bromine, we get an oxonium, and then water, which is formed in the first step, comes along as a base, and it does a deprotonation, and there you go. So now you have your alpha. So you call this an alpha bromoketone, right? So here's your ketone. This is the alpha carbon. So we could say this is an alpha bromoketone. Okay, it's the technical name of this compound would be 2-bromocyclohexanone, but I'm just saying in general terms we would call it an alpha bromoketone. So I do expect you to know the mechanism of this part here, as does everybody else. Okay, ACS expects you to know it and all that kind of stuff. All right, so now that we have that, let's take a look at alpha halogenation if you have an unsymmetrical ketone. That kind of ups the ante a little bit, makes it a little more interesting. So if you have an unsymmetrical ketone like this one here, you'd call this 2-methyl cyclohexanone. Okay, pardon my writing, but anyhow, 2-methyl cyclohexanone. Well, in that case, I'm going to erase that. It's so ugly. In that case, what do you end up with? You see that the bromine going the more substituted position is your major product. And when it's in the less substituted position, it's the minor product. Well, you guys know enough about alkene stability from Organic Chemistry 1 that the more substituted an alkene is, the more stable it is. So if you look at these 2 enol forms, they're both perfectly fine. However, the one on the left is more stable. Okay, and so that's your more dominant intermediate, which is going to act as a nucleophile. So really, all you have to remember is that halogenation occurs faster at the more substituted carbon. That's all you really need to know. And this is something that we ask our students frequently. We'll give them an unsymmetrical ketone. We'll give them the conditions for alpha halogenation. and we'll just say, which side is it going to go to? Okay, everybody with me on that? Give me a thumbs up if you're with me on this. Okay, alpha halogenation. So this is our literally what is shown right here. This is like your first reaction in this whole chapter. So first reaction of chapter 21. Okay, first new kind of reaction that we cover. However, you can actually spruce the conditions up, right? What do chemists do? They can't help themselves. They'll take a product and they'll just throw other things in and see what happens. And it turns out that if you do the first step, okay, you guys already know this, that if you take an unsymmetrical ketone and in the first step you treat it with a catalytic amount of acid and bromine, what do you end up with? You end up with the alpha bromo ketone, which in this case would be this, would be 2 bromo, 2 methyl cyclohexanone, okay? That's what you would get as your intermediate after the first reaction. But then in the second step, what somebody decided is they said, well, what happens if I treat it with pyridine or lithium carbonate or potassium T-butoxide? What happens is those are really strong bases. And so if I treat it with a strong base, it's going to rip this proton and do an E2 reaction. And then I end up with this compound. And we call this an alpha beta unsaturated ketone, right? You guys know that unsaturated means double bond. So this is alpha, this is beta. So hence the term alpha beta unsaturated ketone. All right. So now this is kind of like your second reaction. Okay. It's kind of 2 bits put together. But the bottom line is you make your alpha bromo ketone on the more substituted carbon. Then you put in a base. It can be pyridine, it can be T-butoxide, it can be lithium carbonate. There are other bases that work as well. And then it does an elimination that I have drawn here. And then it gives you the alpha beta unsaturated ketone. And you might think, well, that's boring. That's not all that exciting. Well, it turns out that we're actually going to use these alpha beta unsaturated ketones as reagents later on in this chapter. So it will be of a high interest to us. All right. So that is kind of like your second reaction. It's almost like a 1.5. Okay. It's kind of adding on to the alpha halogenation. You throw in a base, you do an elimination, you get an alpha beta unsaturated ketone. Well, the next reaction is called the Hell-Volhard-Zelinsky. And again, we call it the HVZ reaction a lot. What's cool about this reaction is that you make an alpha bromo carboxylic acid. So if this is a carboxylic acid, right, this is the alpha carbon. After doing the HVZ reaction, you install a bromine at the alpha carbon. So we call it an alpha bromo carboxylic acid. Now, this is not something you need to know for this chapter. However, I know that a lot of you have studied, not all of you, but many of you have studied advanced biology. And so later on, what we're going to see, what's so cool about this reaction, and we don't see it in this chapter, but later, we're going to talk about how you can take this compound and you can make amino acids from it. Okay, so you can take an alpha bromo carboxylic acid and you can use it to do, it's achiral, but it's, hey, you know what? I always say an amino acid is an amino acid, right? So you can do an achiral amino acid synthesis. So, these guys got a lot of fame for that. So the first step is taking your carboxylic acid, treating it with bromine and phosphorus tribromide, right? Remember PBr3? This is phosphorus tribromide. What happens when you do that, you end up with this intermediate here. So after the first step, this is called an alpha bromo acid bromide. I'm not going to write that down because I'm not going to make you remember alpha bromo acid bromide. But you know what happens when you take an acid chloride and you treat it with water, it hydrolyzes it to a carboxylic acid. So in the second step, when you treat it with water, it just blows it apart to the carboxylic acid. And so you end up with your alpha bromo carboxylic acid. I can tell you right now, I've taught this class long enough to know that Mr. Dion, the guy who's teaching you this class, I'm not going to ask you about any of these intermediates. Let me say intermediates along the way. Okay. I will not ask you about the acid halide, enol, and all that. I never ask my students about that. All I want you to know is the Hell-Volhard-Zelinsky, what the reagents are, and that it takes you to the alpha bromo carboxylic acid. The reason I bring up this intermediate, I always mention this intermediate when I'm teaching it, because some students find it easier to remember that intermediate and then they think, well, if I just throw water at it, it's just going to convert this into a hydroxyl group and I'm done, which is totally fine. Either way works, whatever works best for you. But that's the Helmholtz-Zielinski reaction. And again, one of the major utilities of this reaction is using it to synthesize amino acids. And again, we'll look at that later on. So don't stress about it for today. I think it is chapter 24. So in chapter 24, we will study a whole bunch of ways of making amino acids. So do not stress, my friends. It is coming. All right. So what about this alpha halogenation? We saw acid catalyzed tautomerization, and we saw that tautomerization can also be base catalyzed. So why not? So could I do an alpha halogenation under basic conditions? The answer is yes. And the mechanism is actually, I don't like to use the word simple in organic chemistry, but I'd say this is one of the most straightforward mechanisms that you see in the entire class. Okay. So here you just deprotonate, you make your enolate. So this is the enolate. Enolate acts as a nucleophile, you're done. Okay, that's it. So it's just a proton transfer followed by a nucleophilic attack and loss of leaving group in the second step, and you're done. So this is a very important mechanism for you to know. So let's go back a little bit. Let's go back to here. What have we covered? We have covered, if you take your ketone or aldehyde, catalytic amount of acid and bromine, you make an alpha bromo ketone or aldehyde. We went over the mechanism. If it's unsymmetrical, the bromine ends up on the more substituted carbon. Why? Because that proceeds to the more stable enol intermediate. If you throw some pyridine or lithium carbonate or potassium T-butoxide in the second step, it does an elimination to give you an alpha beta unsaturated ketone. And these are going to come up even more. Later on, we're going to see these come up when we study what's called the Michael reaction. Michael reaction, which we won't look at today. We don't have enough time. Then we looked at the Helmholtz-Zielinski, the HVZ reaction, which gives you an alpha bromo carboxylic acid, kind of a weird functional group. And you might be wondering, well, why would you even do that? And again, I told you all will be revealed in chapter 24 because we do a whole chapter on amino acids, and we'll talk about how you make an amino acid from an alpha bromo carboxylic acid. And then we said, well, it turns out that you can also do this alpha bromination using sodium hydroxide as well. It doesn't have to be an acid. Either one is totally fine. And there you go. But what happens is if you do this, okay, now you have this pK of this proton is, let's say, we could just take a guess. Let's say it's 18. Well, then once you deprotonate and you install your bromine, now the second proton is even more acidic. So it makes it even more reactive over and over and over, okay? If you don't follow what I mean, think about it. If you have two protons here, okay? See this proton that I have the blue and the red, okay? Those two protons. Let's say the pK of these, let's just imagine it's around, 18, okay? Well, what causes the pK to be around 18? Well, it's a myriad of factors, but one of them is the electron withdrawing effect of the carbonyl. So now when I put the bromine in, I've got the electron withdrawing effect of the carbonyl, and I've got the electron withdrawing effect of the bromine. And so now this has got an even lower pKa. So what does that mean? If the pK is lower, when you treat it with the base, it's going to react even faster. So we could put here more reactive. Okay, that's even more reactive. And if you're looking at me and saying, well, okay, what's your point? What's so great about that? Well, what's so great about that is that you can do polyhalogenation, okay? You add bromine after bromine. And if you're looking at this and going, what's so great about that? I would have to agree with you about that. However, what if you have a methyl ketone? So this is what we call a methyl ketone, right? We call it that because this is a methyl group. What's attached to a methyl group? A total of 1, 2, 3 protons. So what's going to happen in the first step is it's going to deprotonate and it's going to do an alpha bromination. Then the next two protons are even more acidic. Then it's going to do it again. Then the last proton is even more acidic than the beginning. So it does it over and over and over until you end up with what? Let's see. Let's draw it. You end up with your carbonyl, but now your carbon, instead instead of being CH3, it's now CBr3. Now, what do I know about CBr3? Okay, that's actually a good leaving group. Okay, it's the conjugate base of what's called bromoform. Okay, and that is actually a good leaving group. Okay, you don't normally think of carbanions as being good leaving groups, but this has got 3 electron withdrawing groups on it, 3 bromines, and so it is a good leaving group. So that means that you can take this and you can hydrolyze it all the way to the carboxylic acid. This reaction altogether is called the haloform reaction. The haloform reaction. So let's take a look at the haloform reaction. Again, here's that intermediate that I just drew. What's going to happen is if you're in strong base, it's going to come in, do a nucleophilic attack, and you're going to lose this as a leaving group. Okay, I told you that the CBr3 anion is actually a decent leaving group because it's the conjugate base of what's called bromoform. So this is bromoform right here. And if you're like, well, that sounds a lot like chloroform. It is a lot like chloroform, except it's not called that. It's called bromoform. And it turns out that bromoform has a pKa that is equal to 13.7. So if we think about a carboxylic acid, which has a pKa of around 5-ish, okay, we'll just put approximately 5, the equilibrium is going to lie to the side of the weaker acid. And so after you lose the CBr3 anion as a leaving group, it's going to deprotonate, and then you end up with the carboxylate. So that's why when you do the haloform reaction in the second step, okay, so after the first step, it hydrolyzes this, okay, to the carboxylate like this. And then in the second step, when you treat it with H3O+, come on, pen, it's going to protonate, and your reaction is complete like that. So as far as the mechanism goes, this is just a nucleophilic attack and a loss of leaving group. I'm not really worried about this one all that much. This could show up on a homework assignment, but I've never asked anybody to draw me the mechanism of the haloform reaction explicitly on a quiz or anything like that. So let's take a look. Okay, this is the overall haloform reaction, which is one of the most classic reactions in all of organic chemistry. So you take your methyl ketone. Keep in mind, you've got to have a methyl ketone. Okay, it's got 3 protons. You keep deprotonating it. You add your halogen until you end up with something like CBr3 or CCl3. Then that is going to be a good leaving group. The sodium hydroxide comes in, does a nucleophilic attack. You lose the CBr3 or CCl3 as a leaving group, and then you do a proton transfer to protonate it back to the carboxylic acid. So it's a very useful reaction. Why? Let me highlight it. It's because it's a way to produce a carboxylic acid from a methyl ketone. I'll leave it right here on the slides. Very useful. Okay. In fact, the author of our textbook, David Klein, likes to use this reaction all the time, taking a methyl ketone and making a carboxylic acid. Why? Because carboxylic acids, we learned all kinds of chemistry in chapter 20 that we can use with a carboxylic acid. So again, we call this the haloform reaction, a very, very important reaction in organic chemistry. So with that in mind, let's try a couple of practice problems. I'll tell you what we'll do is we will take a short break because there's a whole plethora of problems here, okay? I have a problem here, 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 another one here, another one here, and another one here. Oh man, I put a bunch in. Okay, so before we get to aldol additions, I put all of these problems in here. I think we should take a second, and take a look at these. So the first one is an alpha halogenation. In the first step, we're treating it with hydronium and bromine, and that's going to give us the alpha bromoketone. You see this ketone is symmetrical. It's 3-pentanone. So this is 3-pentanone. So after the first step, we're going to end up with this compound. So we have our alpha bromoketone. And then in the second step, we're going to treat it with pyridine. And so that's going to give us, so after treatment with pyridine, pyridine is going to do the elimination to give us this compound. Now it's asking for a mechanism here. So let's draw a little mechanism for this now that we have an idea of what the products are, what the product is rather. So let me delete that. And let's see if we can come up with a mechanism. Well, the first step is going to be proton transfer from our acid. So we'll scribble our acid down like this, and we'll put in our lone pairs, and we're going to pick up a proton off of that so that we end up with our oxonium, which is going to look like this. There we have our oxonium ion, like that. So now we're going to do the formation of the enol. So my water is going to come in as a base, right? This is just acid catalyzed formation of an enol. So I'm going to abstract this proton, form the double bond, and there you go, my friends. That is it. I just drew the mechanism for, maybe I could do better than that. I just drew the mechanism for acid catalyzed formation of an enol. So we end up with something that looks like that. Great. Now that we have that, we know that this carbon is somewhat electrophilic. If we put it in the presence of a bromine molecule, Br2, okay, what are we going to have? We're going to have a nucleophilic attack by this carbon, and that's going to install our bromine. So we end up with something that looks like this. There's our oxonium ion. We've added the bromine, like that. Okay, and so the next thing is going to be a proton transfer. And so water is going to come in as my base this time, and it's going to pick up that proton from the oxonium, and that is going to give me my alpha bromo ketone, like that. And now the next step is to treat it with pyridine. So pyridine is my base. So if I treat it with pyridine, come on, pen. There we go. So we'll draw pyridine, which is a base again. So we have our lone pair here. We'll put a proton here. So it's going to abstract this proton. We're going to lose our leaving group, and then it's going to give us the final product, which is going to be this alkene, this alpha beta. So we call this an alpha beta unsaturated ketone, like that. All right, cool. Let's try another one. Alpha halogenation. So we want to take this alcohol and we want to convert it to this alpha beta unsaturated ketone. And so that could be done from the alpha bromo ketone, and that could be made from the ketone, and that can be made from the alcohol. So the first step is going to be to oxidize this using PCC or Swern or whatever. So if we take this with PCC, we're going to end up with cyclohexanone, like that. Then we need to do the alpha bromination. So we need a catalytic amount of acid and bromine. That's going to give me the alpha bromo cyclohexanone, like that. And the last step is going to be to treat it with a base. You could use pyridine, you could use lithium carbonate, you can use potassium T-butoxide. Let's use lithium carbonate just to be fancy. All right, we're going to save this one here. Next one, this is a Helmholtz-Zielinski reaction. So this one is just recognizing this. This is the HVZ reaction. So that gives us what? An alpha bromocarboxylic acid. So we're going to redraw our 5-membered ring. We're going to have our carboxyl group. And on the alpha carbon, we're going to have a bromine now. And I told you that the synthetic utility of this is you do a couple of more reactions and you can end up with an amino acid. Next one, we have benzyl bromide, and then we want to add a carboxyl group onto it. So you see that this is an alpha bromo carboxylic acid, so we would think of doing the HVZ reaction for this, right? If we did an HVZ reaction in the last step, that means that our precursor would be this compound, which I told you earlier today is called phenylacetic acid. And so the question becomes, well, how do I get from here to here? And the answer is going to be with a Grignard. All right, same thing for this one. It's going to be in the exact same vein. You need to make this compound from this. All right, like that. let's see here. Predict the major product when each of the following compounds is treated with bromine and aqueous sodium hydroxide, followed by aqueous acid. So in the first step, we're going to treat it with sodium hydroxide and Br2. And in the second step, we're going to treat it with aqueous acid. This is the haloform reaction. So haloform reaction. The next one, you can clearly see that this one has to come from a carboxylic acid. So we have to have a carboxylic acid like this. And you can make this, right? If you have the carbonyl compound, right, you can do the haloform reaction. So haloform reaction. So you just need to oxidize the alcohol to the ketone using PCC, do the haloform reaction, and then an esterification. The next one is a Schiff base, which you can hydrolyze to give you the ketone with H3O plus. That will give you the ketone. And then you do a haloform reaction, and then you could make an acid chloride, then ammonia to make the amide. And then that brings us to aldol additions.